Mana mana. Mana mana. Mana mana. Mana mana. Mana mana. Mana mana.
7.2 Properties of Rational Exponents. Your essential question: how do you use the properties of rational exponents to evaluate and simplify expressions? This is just a review of all the properties that we learned in Unit 6. So in 6.1, we learned all the properties of exponents, and today we're going to take all of these properties of exponents, the exact same ones, and we're just going to apply it now to rational exponents, meaning exponents that can be written as fractions or thought of as roots. So starting with the product of powers, and if you remember, that property said if you had like bases, which we do here, A and A, those bases are alike, so when we multiply those two bases, we are just adding their exponents. So that's how we get the A to the m plus n. So now let's do an example where we apply this property with rational exponents. Let's say I have 6 to the 1/2 power times 6 to the 1/3 power. Well, as you can see, I have like bases, so I'll end up adding the exponents. So this will be 6 to the 1/2 plus 1/3. Now, in order to add those exponents, well, they're fractions, they're going to need like denominators. I think my least common denominator or least common multiple will be 6. So 1/2 I'll have to multiply top and bottom by 3. And 1/3 I'll have to multiply top and bottom by 2. This is going to give me 6 to the 3, 6 plus 2, 6, which ends up giving me 6 to the 5, 6 power. That's my final answer. That is completely simplified. We will talk about how to recognize whether these are completely simplified. This one is completely simplified. Moving on to quotients of powers. If I have like bases that are being divided, then I subtract the exponents, leaving me with A to the m minus n. So let's apply this with rational exponents. Let's say I have 6 to the 5/2. I divide it by 6 to the 1/2. Well, I have like bases being divided, so I know that I'm going to have to subtract the exponents, leaving me with 6 to the 5/2 minus 1/2. Lucky for me, this time the denominators are the same, so this becomes some pretty simple math. I'm going to have 6 raised to the 4/2, or in other words, that's just 6 squared, or 36. Again, completely simplified, there's nothing more to do there. If these were really big numbers, like let's say 6 to the 17th power and you didn't have a calculator, you would just leave it as 6 to the 17th power. Next property that we'll be using is the power of a power. So if you have some base being raised to a power, and then that power is being raised to another power, like here I have A to the m being raised to the nth power, then I just multiply those powers to get A to the m times n. So now let's of course apply that with rational exponents. And I did some of these in our last notes, so this shouldn't be too foreign to you. And like I said, we've reviewed, this is just a review from Unit 6. Let's say that I had 4 to the 3/2 power, and that was being raised to the second power. Well, then in this situation, I'm just going to multiply my powers, and the numerator and denominators of those powers reduce because I'm multiplying, so I can reduce or divide out common factors in numerator and denominator, leaving me with 4 cubed, and 4 cubed is actually 64. That is completely simplified. Moving on to a power of a product. So if you have two numbers being multiplied together and together they are being raised to that power, then you can actually give that power to each factor of the product. So one of the factors was A, it gets raised to the m power. and the other factor is b, and it gets raised to the m power. All right, so let's go ahead and let's apply this to rational exponents. Let's go with 27 to the 1/3 power times 6 to the 1/4 power, and then that product is being raised to the second power. Each factor, and factors are just the things that are being multiplied together. So one factor is 27 to the 1/3, and the other factor is 6 to the 1/4. Well, each of those factors are now going to also be raised to the second power. So we'll take 27 to the 1/3, and we'll raise that to the second power. And then we'll also take the other factor, 6 to the 1/4, and raise that to the second power. Well, now I'm going to have to use the power of a power property, right? So I've got a power raised to a power, which means that you multiply the powers. So it looks like I'll have 27 to the 2/3 power. And then same thing, I've got 1/4 raised to the second power, or in other words, we're going to multiply 1/4 by 2. Now I can see that this is going to reduce. So really that's just going to be 6 to the 1/2 power. Now I believe there's some simplifying that can be done here. I have a couple ways of thinking about this, and I think what I'm going to do is try and rewrite 27 as a smaller number raised to some power. So 27 is in fact 3 to the 3rd power, and then that is being raised to the 2/3 power. 6 cannot be written as anything times itself any amount of time, so I'm just going to leave that as 6 to the 1/2 power. Now you can see that 3 to the 3rd power raised to the 2/3 power. Well, I'm going to multiply those powers, and the 3's reduce, so I'm really just left with 3 squared times 6 to the 1/2. Couple ways to write this. I'm going to come up here. I'm going to leave that as 9. 3 squared is 9. And you can say times 6 to the 1/2 power. Or you can say this is 9 times the square root of 6. 9 root 6. Okay, moving down to power of a quotient. If you have a quotient, which is a division problem like a divided by b, and you raise it to a power, well then both the numerator and the denominator get that power. 8 over 27 raised to the 1/3 power. Now I'm going to move over because I'm going to do a couple of these examples with you. So let's start with giving that 1/3 power to both numerator and denominator. You know, if 8 and 27 had a common factor, I would start there, but they don't. So I can't actually reduce 8 over 27, so I'm going to go ahead and give that 1/3 power to both numerator and denominator. So this is 8 to the 1/3 power divided by 27 to the 1/3 power. So what this really means is let's take the cube root of 8 and the cube root of 27. I'm going to think about 8 as 2 cubed. And now I'm going to raise that to the 1/3 power. Okay, and then 27, I'm going to think of that as 3 cubed. And then I'm going to raise that to the 1/3 power. So using the power of a power property, I can reduce the 3's and just be left with 2 in the numerator. And using, again, that power of a power property, I can reduce the 3's and just be left with 3 in the denominator. And there's my final answer. You could have also thought to yourself, what's the cube root of 8? It's 2. What's the cube root of 27? It's 3. So you could have actually skipped that other step and just gone from here to there. Let's do 70 to the 1/3 divided by 14 to the 1/3. Well, I don't know if you know this or not, but 70 and 14 actually have a common factor of 14. So I'm actually going to go backwards. I'm going to start, or what I see here is this part of the power of a quotient property, and I'm going to work backwards to make it into 1 fraction raised to 1 power. So I could actually write this as 70 over 14 raised to the 1/3 power. So this is an example where I'm going to try and simplify what's inside the parentheses first. And 14 goes into 70 5 times. So this is really 5 to the 1/3 power, which could also be rewritten as the cube root of 5. Whichever way you want to do it, using radical notation, like I just circled, or the one above it using rational exponent notation. The negative property of exponents, or the inverse property of exponents. Let's do an example using rational exponents this time. So what if I gave you, let's see, how about 25 to the negative 1/2? Well, in order to get that exponent to be positive, we have to do the reciprocal of the base. And the base right now is 25, and the reciprocal of that would be 1 over 25. So now this would be 1 over 25 raised to the 1/2 power. All right, now you're going to need to give that power to each piece of this quotient. So to both numerator and denominator. So this would be 1 to the 1/2, which is really just 1. And then 25 to the 1/2 power. So like I said, 1 to the 1/2, or the square root of 1 is just 1. And the square root of 25, here I'll write that for you, right? Because that's really what 25 to the 1/2 power means. So your final answer here is just going to be 1 over 5. Let's do another example. 7 times, let's do 1 over 4 to the negative 1/2. All right, well, the 7 can stay the same, but the 1 over 4 to the negative 1/2, that needs to be turned into a positive exponent. And in order to do that, we're going to reciprocal the base. So I'm going to leave the 7. I'm going to reciprocal 1/4, which is really 4, raised to now the positive 1/2. And just 4 is being raised to the positive 1/2, which really means take the square root of 4. So I'll write it in radical notation for you, which then gives us 7 times 2, or 14. And my favorite property of all exponent properties is the zero property. The zero property basically says if you raise anything to the 0 power, you get 1, no matter what that is. So just as a quick review, if you have 81 to the 0 power, you get 1. If you have happy face to the 0 power, you get 1. It's really not a rational exponent here. I guess as a rational exponent, you might see it as, how about I'll go 7 to the 0 over 6. 0 over 6 just means 0. So 7 to the 0 power is just 1. Remember, you cannot have 0 in your denominator. That is undefined. So if you had 7 to the 6 over 0, that's undefined. You cannot divide by 0. Now let's talk about simplest form. All right, when it comes to simplest form, you can have no negative exponents. So you always have to apply that negative exponent rule where you turn the exponent into a positive exponent. Therefore, you got to reciprocal the base. You can have no perfect roots under the radical. That's really important. I'll show this to you in a couple of ways. Now, this first example, evaluate the 5th root of 32, might seem really easy to some of you because maybe some of you realize, hey, that's just 2. Well, why is that 2? All right, so if I take the 5th root of 32 and I write it using rational exponents, this would be 32 to the 1/5 power. And 32 is actually 2 to the 5th power. And if you don't know that, get really used to your factor trees. Right, we know that it's 8 times 4, or some of you know it as different factors. 8 is 2 times 4, 4 is 2 times 2, right? So I just got this down on my prime factorization. 32 is really 2 to the 5th power. All right, so I can rewrite 32 to the 1/5 as 2 to the 5th power raised to the 1/5 power. And using the power of a power now, those simplify, and I'm just left with 2. Could you just go straight from here to here? Sure, if you know that. Okay, but where it gets tricky is when you're not dealing with numbers anymore. When you're actually you have these variables raised to these exponents. All right, so let's try x to the 7/6 power. If you can recognize that 7/6 is an improper fraction, and you can turn that into some proper fractions, where maybe you get some whole numbers out of it, I think that's the easiest way to go. And what I mean by that is, within x to the 7/6, there's a whole x of x to the 6/6 power. Now I can multiply that by a like base of x, and remember, when you have like bases being multiplied together, you have to add the exponents. So 6/6 plus what number here would get me 7/6? And that's right, that would have to be 1/6. Well, now x to the 6/6, or x to the first power, and then x to the 1/6, you could leave as x to the 1/6, or you could write it in radical notation. So this would be x times the 6th root of x. Either one works. You also can't have any radicals in your denominator. So this brings us back to rationalizing the denominator, which we've done in the past. So when I look at 1 divided by the square root of 2, there's really not much that I can do to simplify that, but I do notice that I have a radical in the denominator. So in order to undo that radical in the denominator, I'm going to have to rationalize the denominator. And basically what you do is you multiply by some form of that radical so that that radical doesn't exist anymore in the denominator. The easiest way is to just say, let me go ahead and multiply by the square root of 2. Right? Because the square root of 2 times the square root of 2 is the square root of 4, which leaves me with 2 in the denominator and root 2 in the numerator. It's okay to have a radical in your numerator. Now, why does that actually work? So let me rewrite this using rational notation. This is 1 over 2 to the 1/2 power. I need to multiply 2 to the 1/2 power by something with an exponent that'll make that exponent whole. And remember, if I can multiply by a like base, then I just add the exponents. Well, what's an exponent that I can add to 1/2 to get a whole? That's right, it's 1/2. That's why it works here. So really what I got was 2 to the 1/2 over 2 to the 2/2, which really is just the square root of 2 over 2, just like I got. So let's try that now with the cube root of 1/4. So the first thing I'm going to do is I'm going to write this using rational exponent notation. This is really 1/4 to the 1/3 power. And then I'm going to give that 1/3 power to both numerator and denominator, power of a quotient rule. So 1 to the 1/3 power and 4 to the 1/3 power. Now, of course, in the numerator, 1 to the 1/3 is just 1. Okay, so this is just this. Now, I have a radical in my denominator. I'm going to have to multiply by something with the same base, but that when I add the powers together, I get a whole. So let's see, 1/3 plus 2/3 would give me 3/3. Now, whatever I do in the denominator, I have to do to the numerator because it's like multiplying by a fancy form of 1. So now I've got 4 to the 2/3 over, well, this is 4 to the 3/3. You don't have to write this out, but I'm doing it so that you can see it. So this is really 4 to the 2/3 over 4, or 4 to the first power. That's one way that you could write it. You could also leave it in radical notation if you wanted to. So you could say, hey, this is the cube root of 4 squared, or 16, all over 4. Either one of these works. How about I'll leave it in rational exponent notation?
Mana mana. Mana mana. Mana mana. Mana mana. Mana mana. Mana mana.